In this video, we're going to discuss what it means for two events to be independent. So in our last video, we talked about conditional probability, and it seemed like knowing whether or not something happened always affected the probability of something else happening. So like when we computed the probability of E given F, it normally was different than what the probability of E would have been on its own. So the question here is, does that always happen? So does knowing that some event F occur always change the probability that some event E occurs? Okay, and the answer to that is no. And when it doesn't, we say that the events are independent. So a sort of silly example is, suppose that my experiment consists of asking two people, I called them Kaylin and Steve, whether or not they own a Wii. Okay, this might be a bit dated. But if Steve knows that Kaylin answered that she did have a Wii, will that affect Steve's answer? Well, it shouldn't if he's telling the truth. Okay, it shouldn't, since he either has a Wii or doesn't. Okay, so his answer to this question should already be determined. It shouldn't matter what Kaylin answers. Okay, his answer, he already knows his answer. So these events, so that them answering whether or not they have a Wii, these are independent from each other. So in general, we say that two events E and F are independent if the occurrence of one has no effect on the likelihood of the other. Okay, so knowing that, say, F occurred does not affect whether or not E occurs. So using notation, what that means is that knowing that F occurred and then trying to compute the probability of E. Okay, so remember E given F, so we know that F occurred. This doesn't actually change the probability. Okay, so this should be equal to what it was before. So it should be the probability of E. So we say that they do not affect each other. You could also say this the other way. So if I have F given E, this should be the same as the probability of F. Okay, so whether or not E or F happens does not change the probability that the other happens. So there's lots of different ways to check whether events are independent. So you could use either the things that I listed, or there's another more commonly used way, and it comes about by rearranging the conditional probability formula. Okay, so remember the formula. So if I have the probability of E given F, it should be equal to the probability of E intersect F divided by the probability of F. Okay, so this is the normal formula. Normal conditional, conditional formula, okay, for any events. Now I'm going to switch colors. So if E and F are independent, then the probability of E given F is actually the probability of E. Okay, so if they're independent, I have this equality, which means that I have the this side, probability of E, should be equal to this side if they're independent, seeing as how this equals is always true. So I'm going to continue with my blue here. So this implies if E and F are independent, we should have the probability of E is equal to the probability of the intersection over the probability of F. And if we rewrite this, what it says is the probability of E intersect F is actually equal to the probability of E times the probability of F. Okay, so this is what is often used to check whether or not things are independent. Okay, so I'm just going to rewrite all of this. So events E are independent if and only if. Okay, so that means that if any of these three things are true, then they are independent. And if they are independent, then all three of these things are true. Okay, so the first one is that the probability of E given F should be equal to the probability of E. Okay, or the other way around, the probability of F given E should be equal to the probability of F. Or this last one that we just found, the probability of the intersection should be equal to the probability of E times the probability of F. Okay, now just to point out, okay, especially this last one, okay, it's very tempting to use this all the time. It's only true when E and F are independent. Okay, so you want to be careful. Now, another note, if one of these is true, then they all are. Okay, so you only have to check one. Okay, you can pick your favorite. It can depend on the question. I tend to use this one the most often unless they've given me some sort of conditional probability. Okay, but you're welcome to use any of the three. Sometimes it makes sense to use a certain one. These ones come from the definition of independence, and this one is because of how we can rearrange the formula for conditional probability. So let's do a couple of examples, and I picked two that where I hope our intuition will guide us as well. Okay, so we probably should be able to tell in example 2 and example 3 whether or not these events are independent, and then we're going to use the formulas, one of them, to show that our intuition is correct. Okay, but we need to be careful with our intuition because it's not always correct. So in the first one, our experiment consists of rolling 2 dice. Okay, one's red, one's blue. And then we're going to record the results. E, so the event E is that the red die is a 3, and the event F is the blue die is a 2. Are these independent? So hopefully your intuition is telling you that they should be, because E only concerns the red die, and F only concerns the blue die. So knowing that the red die did something should not affect what the blue die does. Okay, but let's find out why. So I'm going to use the last one again. So what I'm going to do is start by computing the probability that E happens. Okay, so because I'm in a uniform sample space, this is going to be the number of way E's happens over the sample space. So the sample space is usually the easier one to compute. So it's going to be 6 times 6. Okay, so this is 6 options for each die. Okay, so we have the red die and the blue die. Okay, so it's 6 times 6 or 36. On the top, I need E to happen, so the red die has to be a 3. So that means that I only have 1 option for the red die, but 6 options for the blue die. Okay, so this is the red die, and this is the blue die. So here we get 1 over 6 as our probability. Okay, now F is going to be similar. So so it's the number of things in F over the number of things in S. And we already know S is 6 times 6. Now here it's going to be the opposite. So the blue die is a 2. So there's 1 option for the blue die, 6 options for the red die. Again, I get 1 out of 6. Okay, now the probability of the intersection is going to be the number of ways that the intersection happens over the number in the sample space. So we know the bottom is going to be 6 times 6. Now here, the red die has to be a 3, so there's only 1 option, and the blue die has to be a 2, because we're in F and E and F. Okay, so this is a red 3 and a blue 2. So we get 1 over 36. Okay, so now what we're going to do is check. So if I take probability of E and I multiply by probability of F, that's 1 over 6 times 1 over 6. I get 1 over 36 because we multiply straight across, which is the probability that I computed for the intersection. So because this is equal to that, so the probability of E times the probability of F equals the probability of E intersect F, we say that E and F are independent events. Okay, just like we thought they would be. Okay, let's try the next one. So here we select 2 cards, one after the other, without replacement. Okay, so I'm going to take one, not put it back, and then I'm going to pick another one. Okay, E is the event the first card is red, and F is the event the second card is black. Okay, are these independent? So here, if we think about it, if I know that E happened, that means I know I took a red card. That is going to make the chances I get a black card on my next pick more likely because there's fewer red cards. I removed one from the deck. So we would suspect that these are not independent. Okay, so let's try and compute it. So I'm going to use the same idea. So probability of E. So I want to get a red card. Okay, well, first of all, my sample space is, you could do 52 permute 2 because I'm doing the cards one after the other. Or I'm just going to do 52 times 51 because there's just 2 cards. Okay, so this first one is card 1. And then I have to take card 2, which can't be the same card because I did not replace. So now in order to be in E, I need to get a red card first. So there's 26 options for a red card. Okay, so this is giving me a red card. And then when I do my next pick, I don't care what it is, but it can't be what I already picked. So I have 51 cards left over. Okay, so the 51s cancel out. I get 26 over 52, which happens to be 1/2. Okay, so there's a 0.5 or 50% chance that I get a red card on the first draw, which makes sense. Now, the probability of F, I think is more complicated, but it actually turns out to be very simple. But I'm going to try to explain it because I didn't think that it was that obvious. Okay, so the sample space is the same. Now here, I need to get the second card as black. Okay, so I want to do this in cases. So I'm going to do that I get a black and then a black, or I get a red and then a black. Okay, so I'm going to do 2 different cases. Okay, so if I get a black and then a black, I had 26 choices for the first black card, and then 25 choices for the second black card. Now, if I got a red and then a black, I had 26 red ones, and then 26 black ones. Okay, now this is what I didn't believe, really, is that if you factor out the 26, I actually get 51 times 26. Okay, so again, I get 1/2. Okay, so what this says is basically do this one first, even though it's second. That's why I didn't like it. But so you pick a black card and then you pick another card. Okay, for the first card. That's why I wrote it in that order, so you can tell. Okay, so if I want the probability of E and F, okay, we actually already did this because we did these cases, so it's actually this case here, a red and then a black. So it's going to be 52 times 51, 26 times 26 on the top. So what you actually get here, if you simplify, is 13 over 51. Okay, so now we want to check. So we take the probability of E and we times the probability of F. So that's 1/2 times 1/2. So that's 1/4. Is that the same as 13/51? It's not. Okay, it happens to be 13/52. So it's very close. Okay, so but it's not equal to 13/51, which means that it's not equal to E intersect, the probability of E intersect F. Okay, so we have the product is not equal to the probability of the intersection. So here we would say E and F are not independent. Okay, so it again supported our intuition, but I chose them like that so that we could see and then also show how to show that our intuition was right. But in general, you want to always show your work for independent. So mutually exclusive is a different one that we talked about before. Remember, it means that the events don't overlap, so they never happen at the same time. It's easier to check that with little to no work. But for independent, you have to show your work. Okay, so you cannot just say, I think they're independent and that be done with it. So we can use the fact that things are independent as well. Okay, so I made this example to both illustrate the difference between mutually exclusive and independent, and also to use what it means to use that it's independent. So if we have events E and F, okay, and the first probability of E is 0.6, probability of F is 0.25. In both cases, we want the probability of E union F. Okay, so I'm going to write above because this is true for both. E union F is the probability of E plus the probability of F minus the probability of the intersection. Okay, this is the pi. The principle of inclusion-exclusion for probability. Okay, this is true for any sets. So if now we also know, maybe first of all, okay, so that we know this one, we know probability of E and we know probability of F. We don't know the intersection, okay, and we want the union. So at this point, we don't have enough information to solve for the union, okay? But if we know that the events are mutually exclusive, then we do. Okay, so mutually exclusive, this means that the probability of E intersect F is actually 0. Okay, so that means that the probability of the union, is probability of E plus probability of F minus 0. Okay, so we know the intersection is 0. So, and we know all these numbers now. So this is going to be 0.6 plus 0.25. So here we get 0.85 for the union. Again, if we know that they're independent, then we also know the probability of the intersection. Okay, so with this extra information, we can also solve. Okay, so if they're independent, remember that that means that the intersection probability is actually the probability of the product of E and F. The product of the probabilities of E and F. So the probability of the union is going to be the probability of E plus the probability of F minus the probability of E times the probability of F. So if we plug all this in, it's 0.6 plus 0.25 minus 0.6 times 0.25. So we get 0.85. Sorry, not 0.85. That's only the two added together. So if we do that all, we get 0.7 as our answer. So knowing whether or not the events are mutually exclusive or independent gives you more information, and in particular it tells you about the intersection, the probability of the intersection. So that's useful. Knowing this fact, oops, I circled it, but knowing this fact is also useful It applies for more than 2 events. Okay, so we can say that any number of events are independent. So for some collections, say E1, E2 to En. Okay, so if they're independent, again, the probability of the intersection of all of them is actually the product of all of them. So probability of E1 times probability of E2, and I keep multiplying until I get to the probability of En. So knowing things are independent is really useful. It makes it really easy to compute the probability for the intersections. Okay, and so we're going to see that in the next example here. So suppose a company manufactures stereo components, and we know that the parts are independent of one another. Okay, this is important. So that means that they don't affect each other. Okay, so 2% of CD players, I'm going to just write, so C is CD player, okay, works. Okay, so 2% are defective. So we know, where do I want to write this? Maybe over here. So the probability of C complement is 0.02. Okay, 3% of amps are defective. Okay, so A is that the amp works. Okay, so the probability of the complement is 0.03. And 7% of speakers work, and there's actually 2 speakers. So I'm going to say S1 is speaker 1 works, and S2 is speaker 2 works. Okay, so and the probability for both, so speaker 1 complement is the same as for speaker 2 complement. They're both 0.07. So for part A, we want to know the probability the system is not defective. So that means that all the parts work. Okay, so all the parts work. So this is what we're looking for, is the probability of C and A and S1 and S2. Okay, so all of them work. And we have all the complements for all of them. So what we're going to do is just do the 1 minus each. So okay, actually I should write this out. Probability of C, because they're independent. So since they told us, and I can't spell, they told us that the parts function independently. So if one breaks, it doesn't affect whether or not the others do. So then to compute this intersection, we can do the product instead. So probability of C times probability of A times probability of S1 times probability of S2. Okay, now to compute each of these, I'm just going to do 1 minus their chance of defecting. So it's going to be 1 minus 0.02, 1 minus 0.03 times 1 minus 0.07 squared, because there's 2 of them. And if you compute that, you get 0.822. Okay, so there's an 82.2% chance that your stereo will work. All the parts will work. Now, in part B, what is the probability exactly one component is defective if you know the stereo doesn't work? Okay, so your stereo is not working. You want to know, is it worth fixing? Okay, maybe if it's only one component, you're going to fix it. So here we're looking for the probability exactly one defective given broken. Okay, so remember we can use the formula. So it's the probability of the intersection divided by the one that we know. So this is at least one defective. Maybe I should have written that above as well instead of broken. So if it's broken, it means that there's at least one defective part. Okay, so we want to simplify the top. So we need exactly 1. So again, you could use a number line if you, like we did before. So you could have 0 defective parts up until 4 defective parts. 1, 2, 3. Okay, so if you have at least one defective, it means that you have either 1 to 4, but exactly 1 is just the 1. Maybe I should have done that in blue. Okay, it's just that 1. So it has to, where they overlap is just that one spot. Okay, so the top is actually the probability exactly 1 defective. And the bottom, at least 1 defective, is too many cases. So I'm going to do 1 minus the opposite, which is none defective, which is what we just did actually in part A. So this doesn't seem so bad. Now the problem is the top is actually hard to compute. Okay, so the bottom is going to be 1 minus 0.822. Okay, so that's part A. The top, I'm just gonna, we have to do cases. I'm gonna write them out. So the first case, okay, is only C complement. Okay, so only C is defective. So that's going to be 0.02, and then 1 minus 0.03, so 0.97, and then 1 minus 0.07, so 0.93 twice. Okay, so the amp is not broken, and the speakers are not broken. Now, maybe I should write here. So this is C complement intersect A, intersect S1, intersect S2. So again, because they're independent, I can do this intersection as the product. Okay, so that, again, you were using the fact that they're independent. Now, it could be that it's the amp that's broken. Okay, so it's A complement intersect C, intersect S1, intersect S2. So here, A is 0.03. The C working is 0.98, and then the speakers working are 0.93 squared. Okay, or it could be one of the speakers. These have the same probability, so I'm just going to multiply by 2 because I'm running out of room. Okay, so this is 2 speakers. Okay, and then it's 1 speaker is defective. I'm not going to say which one because I'm doing for both. So that means the CD player works, so 0.98. The amp works, 0.97. I still didn't have room. Okay, so 1 speaker is defective, that's 0.07, and 1 works, that's 0.93. Okay, so there were still lots of cases on the top, but we can't get around that. But each of them is easy to compute because they're independent. Okay, if you add all those up, you get 0.166 on the top, and the bottom is 0.178. Okay, so there's a 0.932% chance that if your speaker is broken, that it's only in fact one part that's broken. Okay, so let's write that out. So if stereo, if stereo is broken, there is a 93.2% chance that only one part is defective. Okay, so there's a pretty good chance